So the last topic in dimension analysis is model testing of turbines and pumps. So as with many other machines or like any other machines, it is essential from the point of economy of cost and labor to know the performance of a turbine or a pump before it is actually manufactured. So thus a model of the machine similar to the proposed prototype is prepared and tested. Now, the design, shape, and the dimensions of the model can be altered if required without occurring huge expenditure. Okay. Now, similar to other machines, we have again a prototype and its model for turbines and pumps. So, in order to have a complete similarity between the model and the prototype, so these two must fulfill the similarity conditions. So those similarity conditions are the geometric similarity, kinematic similarity, and the dynamic similarity. Okay. Now in geometric similarity, so it is ensured by keeping the ratio of various dimensions in the model and the prototype constant. Okay. So for example, the ratio of width to the wheel diameter. So means if this is the runner of the prototype and this is the runner of the model, okay, so this is the diameter D and this is the width B. So this is for prototype. Okay, so here for model, this is the width and this is the diameter. Okay, so we keep the ratio constant. So that is the ratio of width, that is BP upon dP, should be equal to Bm upon dm. Okay, for geometric similarity, this ratio to be kept constant. Okay, now similarly, in case of Pelton turbine, here we have the jet is coming out from the nozzle and striking the bucket. Now say that jet diameter is small d. Okay, so for prototype we call it as dp and for model we call it as dm. Okay, now further you can write the ratio dp to dp is equal to dm to dm. Okay, so the ratio of jet diameter to the runner diameter is again constant. So all these ratios are kept constant to maintain geometric similarity in the turbines and the pumps. Then the kinematic similarity. Now kinematic similarity means the similarity of velocities, discharge, acceleration. Okay, so you can say kinematic similarity in fluid machines results a constant ratio. It results in constant ratio of velocities, okay, discharge, okay, acceleration at homologous points. Okay. Now the direction of motion should also be the same in the model as well as in the prototype. Means when we draw the velocity triangles in case of turbines and pumps, we draw velocity triangles. So in different velocities, we have different angles. So that gives us the direction of motion of water. Okay. So those directions we also kept constant for kinematic similarity of turbines and pumps. So the directions of motion should also be same in model and prototype. Okay. So the velocity triangles, you can see the velocity triangles for model and prototype, because their directions are same, angles are same. So we can call that as the velocity triangles are similar. Okay, that are similar for model and prototype. Okay, so the ratios for velocities we can write v upon u. Now the meanings are much more clear when you study turbines and pumps. So here you can simply write v upon u for model is equal to v upon u for prototype. Then there is one component flow velocities, vf upon u for model is equal to vf upon u for prototype. Then there is also one whirl component of velocity, vw upon u for model equal to vw upon u for prototype, like this. So such equations hold good for kinematic similarity. Okay. Then is the dynamic similarity. So for dynamic similarity, now if there is dynamic similarity exists, you can say there is a complete similarity between model and its prototype. So this complete similarity or dynamic similarity that we can attain by dimension analysis method. So as we earlier studied that in case of fluid machine problem, we have different parameters. Okay, we have different variables that involve in that particular phenomena. So those variables are head, speed, discharge, power, density, viscosity, diameter, and when we see the equation, there is one more, that is G. So when we apply the dimension analysis on all these variables, we have different set of pi terms. Okay, so in last, we reach at four terms. One is Q upon ND cube. The second term is GH upon N square D square. Third term is P upon rho G H N D cube. And the fourth term is mu upon rho n d square. Okay, so these are the four terms we have. Now, in case of pumps and turbines, as the velocity is very high, so there is a no concept of Reynolds number. So there is no effect of viscosity in the flow. So we can neglect this term in case of turbines and pumps. So fourth term we can neglect. So we left with now the three term 1, term 2 and term 3. Okay. Now further you see for model and prototype the value of g. So g for model is equal to g for prototype, acceleration due to gravity. Now further for model and prototype, if our fluid is water, you can also say rho for model is equal to rho for prototype. Okay, so these two equations also holds good. So again we can write three terms, q upon nd cube. Now term 2 becomes, so g is not there now, h upon n square d square, and the third term is p upon, now rho g is not there now, h n d cube. Now you can see here equation number 2, or sorry, not equation, the term 2 and term 3, these are no longer the dimensionless terms now. Okay, but we can use them in case of turbines in particular situation. Okay, now further we use some alterations now. Okay, so the first term, okay, that we can replace by, so first term divided by under root of second term. Okay, so we take second term as it is. So we replace the first term by first term divided by under root of second term, so that we can write as q upon nd cube. Okay, so into n square d square upon h under root. Okay, so this becomes q upon d square under root of h. So this is now our first term. Okay, this is now our first term. Okay, now we do one more alteration. So the last term, the last term can be replaced by, so last term divided by under root of second term. So that I can write as last term is p divided by hn d cube into under root of n square d square divided by h. So that I can write as p upon d square h raised to power 3 by 2. So this is my third term now. Okay. So either now I have two set of equations now. This is the one set. Equation 1, equation 2, equation 3. Now the another set is, now the one set is this one, yellow. Okay. Now the another set is first term, second term, and the third term. Okay, this is the third term. So term 2 is common in both the sets. Okay. Now there is one more term. So another important term in hydraulic machines, that is in case of turbines and pumps, that is known as specific speed. Okay. So that I can write as ns is equal to, now the under root of first term divided by second term raised to power 3 by 4. Okay, so this comes out to be q under root of n d cube into n square d square upon h raised to power 3 by 4. So this becomes equal to n under root of q h raised to power 3 by 4. Okay, this term. Okay. Now also I can write ns is equal to under root of last term divided by second term raised to power 3 by 4. So this comes out to be under root of p under root of h n d cube into n square d square upon h raised to power 3 by 4. So it comes out to be n under root of p divided by h 5 by 4 raised to power 5 by 4. Now this is the another term I have. Okay. Now the upper term is the specific speed for pumps. I use that term for pumps. And the bottom one, this one I can use for turbines. Okay. So this is the fourth term we have now. This is the fourth term we have. Okay. Now if I conclude all this, I can write now. So the necessary conditions for complete similarity, okay, between the model and its prototype are, so the first set of equation I have h upon n square d square, okay, for model is equal to h upon n square d square for prototype. That is my equation number 2. So that is my first important equation. Okay. Now the second is my equation number 1, my term 1, q and dq. Either this term or either this term. Okay. So I can write as q upon n d cube for model is equal to q upon n d cube for prototype, or Q upon d square h under root for model equal to Q upon d square under root of h for prototype. Okay, equation number 3. Equation number 3 is either this one or this one. So I write it as P upon hn d cube for model equal to P upon hn d cube for prototype, or P upon d square h raised to power 3 by 2 for model is equal to P upon d square h raised to power 3 by 2 for prototype. And my fourth equation, that is the specific speed. Okay, so I write the fourth equation as n under root of p h raised to power 5 by 4 for model equal to n under root of p h raised to power 5 by 4 for prototype. This is for prototype. So I use this equation for turbines. Okay, and the last equation, n under root of q h raised to power 3 by 4 for model is equal to n under root of q h raised to power 3 by 4 for prototype. I use this equation for pumps. Okay, so now you can see in case of turbines, I can use equation number 1, I can use equation number 2, 3, and equation number 4. So for turbine, if I say I use this equation, or in term of this, I can use this equation, or this and this. Instead of 3, I can also use this one. Okay? Now, in case of pumps, I can use this one. Okay? I can use this or this. I can use this or this and this equation. Okay? So, for complete similarity of turbines and pumps, I can use these four relations. So, these four relations I can use as a similitude laws. Okay, I can use them as a similitude laws in turbines and pumps. Okay, so this is all about the model testing of turbines and pumps. Now you can apply these equations in problems, in numericals. Okay, so thank you.